Again, I apologize. I don't have to. I have to finish a certain amount, so I'm not really going over homework too much. But if you really want me to explain something more, let me know. I'll make a video or something explaining about the homework a little bit more if you want me to, if the homework explanation and file is not sufficient. So surface is given. Then these are usually recognized as a collection of x and y and z coordinates, right? Then we parameterize with s and t. What is the most interesting example maybe is that parallelogram hovering in the space, right? If that's a surface, and how are you going to parameterize it? Anybody remember how to parameterize parallelogram hovering in this space? For example, suppose that was R0, and that's one vertex, and here is parallelogram in the space with one vertex there. What's the key ingredients to parameterizing this parallelogram? What is it? This is the vector from origin, right? And what other vector do we need? This one and that, right? Those are called P and Q. Displacement vector, right? So if you have R in general, P, and the plate R there, how would you describe it in terms of vector? R0, you have to go R0, right? Then how many more? What kind of vector? It's a combination of P and Q, right? So, yeah, S times P, something times P, absolutely. And something else times Q, right? So these two parameters give you the location in here. You need two numbers to locate. That makes sense in terms of XY coordinate system. Make sense? That's how you describe all the points in there. Even if it is not origin, you can shift it like that. So that's one example of parameterizing the surface. And using cylindrical coordinate system or spherical coordinate system, you can also parameterize those surfaces. If you look at the spherical coordinate system, what are those two parameters? Theta and phi, right? Remember the spherical about cylindrical coordinate system? There's a theta and z, if you remember. Those two parameters give you the location of some point on that surface, right? So two parameter. So you need two parameters. Gotta understand that part. So once you have that, if you have a surface there, and there's this non-constant fluid density vector passing through, and what is a number of particle passing through that? Maybe at this point it's going to pass through like that. Maybe at that point it's actually passed through opposite side, right? And one will be counted as a positive number of particle, and this will count as a negative number of particle. Who knows how we decide? I mean, if you formulate it like this, which one you get positive, which one you get negative? How can you tell by looking at the formula here which one is relevant to this decision? You get positive and you get negative. The direction of which vector? Normal vector to plane or the surface, right? But where is that part is relevant to the direction of a normal vector to the surface here? RS plus RT, RS times RT, right? Those are the two tangent vector on the surface. Doing the cross product, they give you the direction. And this doesn't change. If it is good parameterization, they're always facing one direction. If it is changing one direction to the opposite, that's a bad parameterization. You shouldn't play with that. So it should be consistent, good parameterization. So there's something sensitive about that. Once you have the good parameterization, everywhere is this positive direction, and that'll tell you you get positive number and you get negative number, right? So, but even if you have a wrong direction, you can interpret usually the answer correctly, right? Because you're looking at the object. Oh, that should be positive number in here, so I'm going to change the number to positive and negative. So you can adjust that later. Make sense? So when we're saying this surface S, that's what this one is, and we're talking about number of particles passing through the surface, it seems like we need to have more information, right? Like which one is our normal vector we chose. So we call this orientation. If I have a surface there, is this our direction of n, normal vector? then that's your choice, and then this number will turn out positive. If someone else doing the same calculation with opposite orientation, maybe they have different RSRT, then it's going to be a negative number, but the magnitude must be the same, right? So we call it oriented surface. There's something called Mobius strip. Have you heard about that Mobius strip? Yeah, you have a strip and you turn it around, twist it around like that, and glue it. And if you follow this thing around, and if you start with the outside, if you loop it on one side and you come back in inside, so there was no distinction of what is inside and outside. So this is typical non-oriented surface. So this makes no sense with a non-oriented surface. It's confusing with a non-oriented surface because it's all going to cancel out maybe, right? If you go around too much, yes. No, it's not optical illusion. It actually exists, and it is possible. Yes, yeah. So the Mobius strip arises in a four-dimensional space, so you have to make sure, are we in this kind of, anti-world that, that are twisted around and glued together. So if this is oriented surface, this thing makes sense. So we only deal with oriented surface. Small, nothing like this. All right. So we call that one, I've been looking at the number of particles, number of particles, number of particles. So we're going to give a name to that. That's surface integral of a vector field. Especially pay attention to that part. Over what? The original surface that is hovering inside three-dimensional space, right? But what do you see underneath this integral? Not S, right? What is this D? That's a parameter. This is where SNT lives. SNT is how we actually parameterize this visual world. So pull it out to a kind of imaginary space. That's SNT. That's what that space is, right? So make sure you understand that part. And then I don't think there's anything that is confusing about this concept. All right? Physicists like to call this one a different name because it's what they care about is a flux of a vector field across the field. So we're going to simply call it flux or surface integral. There is a surface integral of scalar function, but this is what we care about here, vector field. Right? So that's that. And this is just a picture you've already seen that here's a surface, not necessarily flat, not like a parallelogram, and slightly curved, then this calculation is very, very essential. This is non-constant everywhere, and you calculate that, it'll calculate a number of particle flux of that. So what is this? It's particularly in here. This seems like a long vector, right? What is the meaning of this vector? If I choose a small area here, and this is the direction of where the particles flow, right? And how about the magnitude? Means, what's that? That's right. How fast is the equivalent to how many are moving a given period of time, right? So, and we had to do the dot product to correctly measure perpendicularly because it was sensitive. It wasn't that intuitive, though. We have to analyze that. So, here's a new thing. I want you to look at the first statement and realize, oh, that we understand that part. Here is, what is this called? Line integral, right? This is how actually calculate line integral. There are tricky two different ways of using a fundamental theorem of line integrals and Green's theorem. You can calculate this a different way, but none of this is available. Then you're going to calculate like this, right? Just deal with the parameterization. But it doesn't matter which parameterization you use. The integral will be the same, right? In my opinion, that wasn't that intuitive. Even if you bring in the word calculation thing, it's not that intuitive. But we directly calculated it, and two different parameterization. That probably was one of the advanced problem. Show that they're always true. So we forget about the parameterization. We just write it like this: parameterization free notation. Just a curve. Doesn't matter how you parameterize it. This vector field dotted by the velocity vector, this will be always the same number. So they wrote it like this without t in it. That's the parameterization free notation. Now let's enter surface integral. I think it's a lot easier to understand. If this passes through like that, Why does the number of particle passing through has got to do with your parameterization? It's nothing to do with the parameterization, right? Number of particles passing through must be just the same as you parameterize like that, you parameterize like that. Number calculated must be the same, right? So it's easier to believe that, okay, this is a parameterization. There's a parameterization, right? RSRT, makes sense? Then it doesn't matter how you parameterize it. So they decided to write it parameterization free notation. So before there was a D, correct? That's a parameter space. This is actual space S you see in that orange color. And that's a vector field, has nothing to do with the parameterization. It's position dependent object. And here the N is a normal vector. And if it's parameterization free, you better enter unit normal vector, right? Otherwise, what normal vector are you talking about? There are infinitely many. Which are you talking about? This must be unit normal vector, so it does not depend on anything. Then it's unique. Only that it's your choice of which one is the direction of you. That you have to give it, so that's the oriented surface. Then that's notation, but they throw in this weird dA thing because there's no indication inside. There's this like infinitesimal in there. So they have to throw in something. Rather than dn, they decided to use dA, which is the area of some parallelogram there. Okay? So that's their parametrization free notation. So they're going to write it like this. But whenever you see that, you parameterize the surface, you enter this one. This is actually how you compute. Just like the line integral, there will be a theorem that allows you to calculate this surface integral vector field, not using this one, but even slightly better method if phi is a special one. All right? For line integral, what kind of phi is a special so that this calculation gets easier? What was that? That's right, conservative or gradient vector field. Something like that analogous notion is going to be here. But right now we just focus on this parameterization we call the direct calculation. Make sense? So make sense out of this notation? Alright, this already mentioned one time in Friday class and it was mentioned a couple of times in the homework. The special parameterization called Manja Parametrization. This is if you can isolate z equals f of x, if the surface is, you can isolate z or you can isolate x or you can isolate y, then it's going to written like this, right? Z equals with a neat formula, you know, preferably without any square root, things like that. Then parameterization is easy. The other two, it gets a free, you can do whatever you want with that, and z is just a dependent on that. If it's especially like this, you call it Manja parametrization. Right? If you can isolate like this. What was a typical example I've been using? With surface here? Was elliptic paraboloid. The z equals x squared plus y squared. What are the z equals x times y? Z equals ax plus by. Those are plane, those things, right? But there are other quadric surfaces. If you try to solve for z, then you have to do plus minus root. That's inconvenient. In that case, maybe we look for different parameterization. All right. If you play with this Manja parameterization, turns out this calculation of RS cross RT is always the same, and you don't want to repeat that over and over, right? Turns out this guy is a negative FS, negative FT, and comma 1. You probably remember when you calculate in the homework, and this is always the way it is. Especially the z component is 1. So if you dot it with this guy, right, you get this one, right? Negative PFS, negative FT times Q, 1 times R, right? So I want you to remember this formula. If it is Manja parameterization, many examples in the book, in the exercises, Manja parameterization is available. Then you don't have to do all the cross product. Boom, you just go there and calculate quickly. Okay? If it is not simply S and T, it's more about cosine S in there, sine T in there. If it's not like that, it's not Manja parameterization. You have to calculate this one. Right? Make sense? Would that be a good exercise? Let's try that. I didn't find it, but let's write down. Don't look at your note and see if you can remember this one. So if x is S, y is t, and z is f of x s t, how is this surface S? maybe I should write S is a surface there, given by this parameterization. What is NDA? That's a parameterization free notation, right? What is this one? Where vector field phi is given by P component, Q component, R component, like that. The question is that this is a parameterization free notation. Can we enter parameterized the version of this formula? That was the question. All right, was that okay? Yeah, maybe you're just going to memorize this one directly, or maybe you're going to memorize this formula. That's how I actually do it. That's the normal vector, and the dotted comes a bit more natural. However you do it, it's going to help you to deal with the problems in the test if you can get to that quickly. All right, any question? Here's your exercise number 2. All right. You see the relevance of this problem? What we just to what we just did? What's the relevance? The surface is given in non-parameterized form, right? This is a Cartesian equation, not parametric equation. Then you have to turn this one into a parametric equation, right? What kind of parameterization is available? Manja parametrization, right? So use Manja parametrization. It's already isolated like this, but I would probably choose a version like this in the test, right? And then you isolated Z, and then enter Manja parametrization. This is your exercise number 2. Since the integral is, actually calculating integrals is simple, we'll just formulate it into a parameterization integral, and we'll stop there, not really calculating all the way down to save us time. All right, how is it? Yes. Yes, yes. Why is that negative? They're both negative, right? Yes. Yeah. Sorry about that. Here's a negative there. Here's a negative there. 1 out of 2. That's what I got. Okay. Thank you. All right. Piece of cake, right? Yeah. In terms of what to do, that's simple. It's the meaning of this is so complicated. All right. This is a not Manja parametrization. Could be a bit challenging, but let's try it. All right. Here's the same vector field and same integral, surface integral of that. Just S is different, right? What is it? Parallelogram is region formed by the, what is this? A position vector P, position vector Q. So if I give you the picture, here's vector P, here's the origin, and here's the vector Q, and there's the origin, and there's this parallelogram formed by this one, right? That's our S. That's a flat plane. All right, what is the number one thing we have to do? What's that? Parameterize, is that what you said? Yeah, parameterize. Parameterize S, right? With a little s and a little t, and write down, oh, s varies from where to where, t varies from where to where. Once you have a parameterization, what is the next thing we usually have to compute? Just be ready to calculate the integral directly is usually, we got to prepare this one, right? Right, that cross vector, the cross product is in there. So at this stage, if it is prepared, I think it goes smoother. So do that part first and compute the flux calculation, flux of the vector field. This is exercise, right? Thank you. Exercise number 3, right? All right, how was it? You all right? Any question? Because it's a flat, your RSRT and the way we parameterize it turns out to be constant. But if it is curved, you will have SNT in it, just like Manja parametrization we just did. Okay? So I don't know if it is in the correct parameters orientation, but definitely is in the direction of P to Q. P and Q is in this direction. If you use a right-hand rule, that goes up like this. So you really have to sketch this two vector and which way we're facing this, where this RSRT is facing now. Any question? Okay, so that's how you calculate the flux of a vector field directly using the parameterization. And often most difficult part is actually getting the parameterization correct.